Hello everyone, I'm Akhilesh Kumar Srivastava from ABES Engineering College, Ghaziabad. In today's lecture, I'm going to discuss about a concept of the traversal in the graph, which is known as the depth first search. In short, we say it DFS. We already have discussed about the BFS and its application. As BFS has so many applications, hence the DFS also has multiple applications. We will discuss all those applications one by one, but beforehand, we must have an idea about the DFS, the basic concepts of the DFS, and how to program the DFS will be in my agenda point for this lecture. So let's take a graph. This graph is the undirected graph, and we should first find out the adjacency list corresponding to this graph. So let us first try to draw the adjacency list of this graph. For drawing the adjacency list, I am making the labels for the edges in this graph. Let's say 0 to 1 edge is E1, 0 to 2 edge is E2, 0 to 4 edge is, let's say, E3. 1 to 2 edge, let's say that is E4. 2 to 5, the edge is, let's say, E5. 3 to 4, let's say the edge is E6. 4 to 5, let's say that edge is E7. And then 4 to 6, the edge is 4, 6, 8, E8. Now the connection from the 0 for the even edge will be 0 to 1. Similarly, the connection will be added in 1 to 0 also, because this graph is undirected graph. So for any of the undirected graph, the connection will be both ways. It means if I am taking up the edge 0 to 1, then the connection will be from 1 to 0 and 0 to 1 both. Now I'm taking the E2 edge, and the E2 edge has the endpoints 0 to 2. So there will be a connection from 0 to 2 and a connection from 2 to 0. Similarly, if I am picking up the edge 0 to 4, then there will be a connection from 0 to 4 and a connection from 4 to 0 as well. For E4, the connection is 1 to 2. So the connection will be from 2 to 1 as well. For E5, we have a connection from 2 to 5. So another connection will be from 5 to 2. Next, we have the edge E6, which is 3 to 4. So the connection is from 3 to 4. And the connection will be represented from 4 to 3 as well. Next edge we have E7, which is 4 to 5. So connection has been added for 4 to 5, and hence it will be added in 5 also. So 5 to 4 is another connection. For E8 edge, we have the connection from 4 to 6, and the connection will be added from 6 to 4. So this 7 is not required here, because we only had the vertices from 0 to 6. Now for performing the depth first search, we will first pick the first vertex that comes in the sequence. Here the first vertex that comes in the sequence is 0. So I make the status vector, and that status vector will let me know about the status of the vertex. So initially, none of the vertex has got visited. So the status of each of the vertex is set as 0. So I'm making a status vertex, and in this status vertex, the status of every vertex is set as 0. The very first vertex that is going to be visited is 0. So its status is set as 1, and it is marked in the visited vertex. The first connection from 0 to 0 is 1. So I mark this as visited. I apply a dot ahead of this one vertex, just to make sure that this vertex has been marked visited. This is added in the DFS sequence. And rather than going to 2 and 4, I will start exploring the vertex 1. So this is what the difference between depth first search and BFS is. If it were the BFS, then we would have taken 2 and 4 after this one. So since this is depth first search, we'll pick a vertex and we'll go in its depth. So the vertex number 1 is picked up. The connection from 1 is, the first connection from 1 is 0, and the vertex number 0 is already visited. So we'll see the next vertex, that is 2, and 2 is unvisited. So I will visit that vertex and we'll mark that visited in the DFS sequence also. So both the vertices from 1 means 0 and 2 have got visited. So since I have picked this 2, I'll go in the depth of 2. So 0 is already visited, 1 is already visited, 5 is not visited. So I will now see the status of 5, will mark it as visited, and 5 comes in the DFS sequence. So I will now see the connection from 5. So the connection from 5 is, first connection is this 2, which has already got visited. Next connection is 4, which is not got visited. So let's mark this vertex as visited. And let's say this is 4 in the DFS sequence. Going into the depth of 4. So from 4, the connection is 0, already visited. Next connection is 3. It has not got visited. So I will now visit this vertex 3 and will mark this in the DFS sequence also. I will now go in the deep of, or the depth of this 3. So from 3, the connection is 4, which has already got visited. So there are no more connections from 3. So it means that I will have to come back from 3 to the vertex which is called for the depth first search for the vertex number 3. So I will move back to this 4 because 4 has actually called this 3. So from 4, the connection 0 and 3 have already got visited. We will now see the connection 5. The connection 5 has already got visited. So we'll now see the connection 6. This has not got visited. So I will now mark this as visited and we'll add this in the sequence of the visited vertex. And we'll now move to 6. The only connection from 6 is 4 and the vertex number 4 has already got visited. So we will have to backtrack and reach to the node number which is called 6. So 6 was called from 4. So I'm backtracking and reaching to 4. All the connections from 4 have got visited, 0, 3, 5, 6, everyone. So I will move back to the node which is called 4. So that is 5. So I'm backtracking to 5. Every vertex which is connected to 5, 2 and 4 have got visited. So I will backtrack to the vertex which is actually called 5. So that is 2. I'm backtracking to 2. Every connection from 2 have got visited, 0, 1 and 5. So I'll backtrack to the vertex number which is called 2. That is 1. And then every connection from 1 means 0 and 2 have got visited. So I will backtrack to the vertex which is called 1. That is 0. From 0 we have seen connection 1. Now we'll see the connection 2. This vertex has already got visited. Then we'll look at the connection number 4, which has not got visited, which has already got visited. So it means that every connection from 0 is complete. And finally, I'll go to the calling function, which is called the DFS with the vertex number 0. It means the main function, which is called the DFS. So DFS is complete, and this is the DFS sequence. Let's take another example and do the DFS once again. So here we have 7 vertices in the graph, 0, 1, 2, 3, 4, 5, and 6. Let's mark the edge numbers, E1, E2, E3, E4, E5, and E6. Let us first draw the adjacency list for this. So 0, 1, 2, 3, 4, 5, and 6. These are the vertices. For E1 edge, the connection is from 0 to 1, and hence the connection is from 1 to 0 as well. For E2 edge, the connection is from 0 to 4, hence the connection is from 4 to 0 as well. For E3 edge, the connection is from 1 to 2, hence the connection is from 2 to 1 as well. For E4 edge, the connection is from 2 to 3, hence the connection will be from 3 to 2 as well. For E5 edge, the connection is from 3 to 4, hence the connection will be from 4 to 3 as well. For E5 edge, the connection, sorry, for E6 edge, the connection is from 5 to 6. So the connection is from 5 to 6 and 6 to 5 as well. So this is the adjacency list for the given graph. Now, since we already have made the adjacency list, we will now take the status vector, and the status vector size will be 7, the same as the number of the vertices in the graph. So 0, 1, 2, 3, 4, 5, and 6. This is the status vector. And every vertex status will be marked as 0, means unvisited. We will first pick the first vertex in the sequence, that is 0, and mark its status as 1. So from 0, the first connection is 1. 1 has not got visited earlier. So I'm going to mark this 1 as visited, and we'll add 1 in the DFS sequence. We'll now go in the depth of 1. So from 1, the connection is 0, which is already visited. We'll go for 2, and 2 is not visited. So we'll mark this as visited. We'll now go in the depth of 2. So the connection from 2 to 2 is 1, which is already got visited. Then the next connection is 3, which is not got visited. So let's mark it as visited and add it in the DFS sequence. Let's go in the depth of 3. So connection from 3 is to 2, which has already got visited. Next connection is from 3 to 4. This is not got visited. So let's mark it as visited and add it in the DFS sequence. From 4, the connections are 0, already got visited. 3 also has all got visited. So we have looked for all the connections from 4. So we will backtrack to the vertex number, which is called this 4, that is 3. All the connections from 3 has already been seen. So we'll backtrack to the vertex which is called 3, that is 2. Similarly, all the connections from 2 is over. So we'll move to the vertex number which is called 2, that is 1. Similarly, all the connections from 1 is complete. So I'll move back to 0. From 0, we can see that 1 has been seen, 4 has not been seen, but 4 is already visited. So we cannot move ahead with the 4. So 0 has also seen its all connections. So the DFS suggests that if there is no, if it looks like that there is no connection forward, then you should see the status of the vertex in the sequence, because you have started the DFS with a 0 number vertex. Now you see the status of 1 number vertex, it is visited. 2 number vertex, it is visited. 3 number vertex, it is visited. 4 number vertex, this is visited. 5 number vertex, this has not got visited earlier. So you will mark this as visited, and you will add this to the DFS sequence, and then start into the depth of this 5. So the connection from 5 is 6. 6 has not got visited. So let's mark the 6 as visited and add this to the DFS sequence. From 6, the connection is 5. 5 is already visited. So you will move back, or you will backtrack to the vertex which is called this vertex number 6, that is 5. From 5, you have seen all the connections. So you will backtrack to the calling function, and the calling function has seen the status of 0, 1, 2, 3, 4, 5, everything, but it has not seen the status of 6. So let's see the status of 6. This has already got visited. So we have completed our DFS, and this is the DFS sequence. Had there been 2 more vertices, let's say there are 2 more vertices, 7 and 8, and the connections are like this, or let's say we have 1 more vertex, 9 also in the same graph, then we must have added 7, 8, 9 in the adjacency list. Let's say this is E7 vertex, E7 edge, this is E8 edge, and let's say this is E9 edge. So from 7, we have a connection to 8, and from 8, we have a connection to 7. Corresponding to the E8 edge, the connection is from 7 to 9, and then from 9 to 7 as well. For E9 edge, the connection will be from 8 to 9 and from 9 to 8 as well. In the status vector also, there will be 3 more entries corresponding to 7, 8, and 9. All these are 0. By the time we have seen the 6, so after 6, we will see the 7. And the status of 7 is 0. So we'll mark this as visited. And this is added in the DFS sequence. From 7, we have a connection to 8, which is unvisited. So we will mark this 8 as visited and we'll add that in the DFS sequence. The connection from 8 is to 7, which is already got visited. The next connection is up to 9. This has not got visited, so you will mark this as visited and we'll add in the DFS sequence. You'll go now in the depth of this 9. So from 9, the connection is 7. And 7 is already got visited. Then you will look for 8. 8 has also already got visited. So you will backtrack to the calling function, or it means 9 was called from 8. Every connection from 8 has been seen. So you will now backtrack to the one which has called 8. So that is 7 number vertex. From 7, you have seen 8. Let's now see 9. The 9 has already got visited. So you will now move to the calling function. The calling function has already seen the status of 7. It will see the status of 8, which has already got visited. It will now see the status of 9, which has also got visited. So this completes the DFS, and this is the DFS sequence corresponding to the given graph. Now let's try to write the algorithm for this. So it looks like that there will be two kinds of the function. It is suggesting that we have to go into depth of the picked vertex or the just picked vertex. It means that we will go by the recursion. And when we are having no way forward, we are moving back and we are looking at the status of the vertex one by one. So there will be an iterative version also. So let's take a DFS algorithm. In the DFS algorithm, we have been given a graph. Let's say the adjacency list of the graph is given. And let's say the total number of vertices in the graph is n. So we will first take the status vector. The size of the status vector will be n, and every single vertex will be initialized to 0. So if I'm initializing like this, so first vertex will be initialized to 0, and all other vertex will also be initialized to 0. And then I will apply a loop to check the status of all the vertices. So if the total number of vertices are n, the vertex numbers we are assuming that will be from 0 to n minus 1. So for I is equals to 0 to n minus 1 2, if the status of vertex number I is 0, then you will start the recursive version of the DFS. Let's say DFS recursive is the function wherein you will pass the vertex number I and the status. Fine. So if the status of the given vertex is 0, you will start calling the DFS recursive function. So now let's write the DFS recursive function. So in the DFS recursive version, what we have I and we have the status vector. Since we do not know the size of the status vector, so the size of the status vector should also be passed here. Now you will visit this vertex number I. So you will first write the vertex number I. You're displaying this. After this, you will set the status of ith vertex as 1, means visited. Then you will see all the connections from I. So for each I that is adjacent to, for each j, let's say, adjacent to I. So we have not added the adjacency list, so that should also come here as a parameter. So in the DFS recursive function, we'll pass the adjacency list also. So for each of the connection which is adjacent to you, you will check the status of j. So if the status of j is unvisited, it means if the status of vertex is 0, In that case, you will call the DFS recursive function with the same vertex j. So if we are calling it recursively, it simply means that we are doing it into depth. So this way, when this DFS recursive function cannot go into depth, you will backtrack to the DFS iterative version, and this loop will ensure that none of the vertex gets unvisited. If there are multiple connected components in the graph, in that case, we will have to call DFS recursive function from the iterative version many a times, or as many times as the number of connected components are there. So let me write the keywords which are required to write the algorithm. Similarly for the recursive version as well. Now we have already done with the algorithm part. Now let's try to write the algorithm, or let's try to convert this algorithm into the program. So let's say we have the main function, and this main function, we already have written the code for taking the input for the graph. Since we are taking the undirected graph, so we are taking the adjacency list. If the edge is AB, then in A adjacency list B is added, and the B adjacency list A is added. We're then displaying the vertex or the adjacency list of the vertex, and then we are calling the DFS function. Now, in the DFS function, this is the iterative version of the DFS function, which says that we have the adjacency list and the number of the vertices. We are taking the status vector, and the size of the status vector has been set as n. All entries of the status vector is initialized to 0. Then as we have written the algorithm, we need to have the traversal, or we need to go to every vertex, and let's check if the status of that vertex is 0, then we're calling the DFS recursive version. In the 22 number line, we are calling the DFS recursive version. In this recursive version, the parameters which are passed are adjacency list, status, and the vertex from which I am starting the recursive call. In the DFS recursive function, we have accepted this, and since this status vector will keep changing, hence we have the call by reference. There will be no change in the adjacency list, but there will be change in the status, hence the ampersand status. It means that whatever changes we are making to status will be marked in the original one. So as soon as we enter this DFS recursive function, the status of the ith vertex will be set as 1. We'll print this vertex, and we'll look at all the connections from this vertex I. So for all the connections of this I vertex, we are looking at the vertex status. Let's take this x is equals to adj ij. It means this is representing the connection from the adjacency list. If the vertex status is 0, we will call the DFS recursive function with this vertex itself. So that vertex is x, which is adjacent to I, and the status of that vertex is 0. Hence, we will call this function recursively. So wherever this recursive function will not be able to go into the depth, we will come back to the DFS iterative version. And this is checking the status of every vertex one by one. Whichever vertex would not have got visited, this will start the recursive function from that vertex itself. So let's try to run this algorithm. So we are going to see the graph on the right hand side, and we'll try to find if this gives us the correct output. So the total number of vertices in the graph are 10 from 0 to 9. The number of the edges are 9. The edge 1 endpoints are 0 and 1. Edge 2 endpoints are 0 and 4. Edge 3 endpoints are 1 and 2. Edge 4 endpoints are 2 and 3. H5 endpoints are 3 and 4. H6 endpoints are 5 and 6. H7 endpoints are 7 and 8. H8 endpoints are 7 and 9. And H9 endpoints are 8 and 9. So you can see that this is the adjacency list, and the order of the DFS is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have seen this here also. So that means that we have implemented this algorithm correctly. You can test it. You can run this code on your system as well for the practice. These are the references for this lecture. Thanks for watching this video.